We've now reached the middle of the 20th century. The 20th century saw some very, very profound changes in everything. The First World War and the Second World War shook a lot of people's faith, among other things in science. There was an intellectual change that began after the Second World War that is in many respects as big for its implications for human thought and the manner in which science is conducted as the birth of scientific modernity around the time of Descartes, Galileo and Newton. Literally, it's that big. We'll refer to this change here as the cognitive revolution, given our particular concerns in this course. The alterations post-Second World War are so far-reaching that there's no good single name for this. And the Second World War ended in 1945, and we're talking about a change in the intellectual climate and in the way people spoke about themselves that is spread over several decades. So the cognitive revolution is in full swing by the 1960s, but these kinds of vast transitions don't have simple edges to them. The birth of scientific modernity itself is spread over about 200 years. So it'll be a while before we know what actually happened here. But there was a conjunction of developments in mathematics, reasoning, engineering, philosophy, linguistics that came together and that provided a novel vocabulary which simply didn't exist before. A lot of it revolving around such notions as computation and information. This gave birth to what we now refer to as the computational theory of mind, which we will be exploring in some depth. And for reasons that I hope will eventually become clear here, this is the point at which the scientific study of language, as understood by Noam Chomsky and his colleagues, moved central stage in theories about mind. And not just everything about language, for language is incredibly rich, as we'll see in the next couple of lectures, but specifically the structural elements of what we call syntax, which determines the order in which words can be placed and rearranged within a system called English, for example. That particular lens turned on language played a huge, huge role. Now we'll meet Chomsky more fully when we turn our attention to language in 2 lectures' time. But it's useful here at the outset to know some of the principal foundations of Chomsky's view, which became relevant in this general change. For one thing, Chomsky represents a strongly rationalist pushback against the strongly empirical excesses of the behaviorist. From a rationalist perspective, remember the role of experience, the senses, encounters with others is downplayed, and a great loan is taken out on biology as providing a kind of an innate readiness to develop human capacities, and specifically language, taken then as a central marker of our species, is assumed to be largely innate. What that means, we'll explore later. The assumption here is that by virtue of biology, all humans possess some kind of organization somewhere within them that allows them to rapidly learn language so that they have the basics of all possible languages inside them. This is called a universal grammar. And so the learning task of the child is simply to select from the environment those features which are necessary to distinguish this language from that language. These are concerns that we'll return to when we study language, but I want to emphasize that they played a role together with developments in thinking about mind, using the computational metaphor, using the language of information, and feeding in to the development of a worldview and intellectual picture which is not really owned by any one discipline at this stage. Chomsky, who's misspelled on the slide, worked closely for some years with a philosopher called Jerry Fodor, who passed away a few years ago. They came to articulate a common perspective. Chomsky as a linguist and Fodor as a philosopher. And I hope the reasons for the close collaboration will become clear as we explore here first Jerry Fodor's work and then later Noam Chomsky's work. Fodor put out two very influential books. One is called The Modularity of Mind. Now, here we see mind again being reified. That is, there's an assumption made at the start that there's something called mind that we can talk about. Fodor doesn't say specifically what it is. And in fact, Fodor's approach is to divide up this already poorly formed object into several different things. And with this, he's reviving a very old idea from psychology before psychology was ever a science. The idea that human reason and intellect is composed of distinct faculties. The faculty of reason is distinct from the faculty of language, is distinct from your ability to engage in carpentry, for example. That is a very old idea, not particularly scientific, but just as a way of thinking about the fact that we have various skills, capacities, and abilities, some of which seem to have little to do with others. Jerry Fodor resurrected this here with the modularity of mind in suggesting that each such, when you could identify one such faculty, one had identified a computational unit which accepted information from outside, processed it in its own way, and did its own task. So if we're talking about the faculty of language and as a whole, then we would be talking about just processes relevant to language, not processes relevant to color perception, for example. Now, exactly which modules these are has never been resolved. It was never resolved hundreds of years ago. But this way of thinking about human capacities and skills fitted into the emerging view of problems as admitting of computational solutions by a means of divide and conquer. So if you have a complicated problem and you can divide it into relatively independent parts, and then you can solve the independent parts, then when you put them back together, you've got a solution. That assumes you can separate these in the first place. But this is very much the approach taken by software programmers. And programming and the construction of software and the distinction between software and hardware have only just entered the vocabulary here. So there's an underlying metaphor here, which is the computer. Computers carry out rule-based manipulation of elements which are in themselves meaningless, bits of ones and zeros. But in the rule-based transformation of sequences of ones and zeros, then a particular group of ones and zeros, a representation of something, can be transformed. This is the underlying metaphor which became so fecund. Now, as well as this book, he had a second book which was equally influential, and this is The Language of Thought. And with this, he draws the emerging discipline of generative linguistics with no at its heart. He takes all these concepts with which Chomsky is building syntactic theory. Syntactic theory is concerned with the rule-based manipulation of symbols, allowing some rule-based transformations of strings of symbols, disallowing others. And in this way, if the first string of symbols has some meaning and is transformed according to rules, the resulting string has some altered meaning, and the change in meaning is a product of the application of rules. This kind of thinking was turned onto thinking itself by Jerry Fodor. Now, thinking has no accepted definition. Like mind, I'm afraid we have to work with the fact that there is no readily accepted definition of what thinking is. Fodor here is trying to pick out some aspects of a sort of familiar aspects of your internal mental life, as it were, which are language-like. So he's talking not about thought in general, he's talking about thought which is similar to language. Thought which has sequences, thought which might be verbally expressed. Imagine you're walking past the kitchen and you think to yourself, I'd love a pie. It's the kind of thing you might think and say out loud. To the extent that the thought and that involuntary verbal utterance are the same thing, then the thought is structured much like a sentence. I would like a pie as a thought doesn't seem to differ from I would like a pie as a sentence. Now, there's many aspects of what we might more generously include in thought that are not going to be addressed by this. And Fodor had to roll back some of his claims. Nevertheless, this introduction of the formal means with which language is studied as sequences of symbols transformed by rule becomes now a guiding light in the development of theories within what will become the discipline of cognitive psychology. So, by the middle of the 20th century, we've got this huge revolution. The computer has really been invented in its common form. There's a chap called John von Neumann who invented what we now think of as the basic architecture of a computer, with a central processing unit with registers, memory, inputs and outputs. Computation had been discussed for hundreds of years, and there had even been artificial computing engines built before. But von Neumann placed all this on a formal foundation, which was to give rise to what we now know as the modern computer. And with that, the distinction between software and hardware, so that you can talk about the software to some extent independently of the hardware on which it runs, and of programs that provide means of thinking about how specific tasks are solved. This was all new. Furthermore, at Bell Laboratories, a wonderful guy called Claude Shannon had come up with a theory of information. The information as a word, as a vague idea, had been around since forever. Shannon used a very specific interpretation of the notion of information, which had to do with the amount that needs to be passed from a sender to a receiver in order to produce novelty in the receiver. So if I just shout and everything I shout is something you've heard before, in a sense there's no new information in what's coming in. So Shannon's notion of information is very specific and refers to very specific circumstances. It has since been wildly expanded, misinterpreted, misapplied. Shannon himself was horrified at the way people treated this word. Information is a term that means different things in different contexts, but the fact that there was now a mathematical theory of information became extremely important. And this development together, which was going to have knock-on effects in everything, including technological development, the ordering of societies, and so on, also gave birth to this computational theory of mind, to cognitive psychology, and to a dream of something that was called artificial intelligence. And we need to say a little bit about that term now with some historical perspective. You read a lot about artificial intelligence in the papers today. You might be asked to support or not support it. It might be contentious. You might see it as a bright hope for the future. What's the it when we speak of artificial intelligence? Well, the meaning has greatly changed over the last 50 years or so. At this early period in the 1960s, it became possible to think that one might program a computer, which is a physical symbol system manipulating system, so that it appeared to be intelligent by some definition of intelligence. This was made into a formal hypothesis by Alan Newell and Herb Simon in the physical symbol system hypothesis, who suggested that such a computational system had the necessary and sufficient means of what they called general intelligent action. The guiding intuition here is that symbols is a very broad set of things. It can refer to sequences of ones and zeros, sequences of letters. Almost anything can be a symbol. A symbol stands for something. And when you combine symbols, in their combination, they acquire meanings to an interpreter. And by rearranging them, you transform those meanings. It's a very, very powerful idea. But what I want to alert you to is that the notion of intelligence here is not defined. There is in play in the 1960s a vague notion that humans are exceptional by virtue of reason and language, and that it is in the carrying out of reason that they display their most human-like qualities. And reason here means things like solving maths puzzles, winning chess games, all highly intellectual activities of a kind that are preferred by a kind of Western European, highly educated, privileged kind of community. I know you've probably heard since then people have designed other kinds of meanings for the word intelligence, including things like emotional intelligence. What I want you to know is the word never had any meaning in the first place. Any scale to measure intelligence is a methodological fantasy. And the word has, at this stage, means the pipe dream of transplanting a vague and ill-defined notion of consciousness onto a toaster. Since then, there's been lots and lots of work in the field, and these days the term artificial intelligence has nothing to do with those original dreams. When you see terms like data science, machine learning, and artificial intelligence combined today, what they are part of is an engineering, a form of social engineering, which serves commercial purposes, political purposes, and has nothing whatsoever to do with this vague and ill-specified notion of intelligence from the 60s. The kind of problems they were looking at would be this. This is a classic children's problem called the Towers of Hanoi. If I could get the slide to animate. The task is to move all the dots from one stack to the most distant stack, always moving one disk at a time, never placing a larger disk on a smaller disk. It's a little logical puzzle. I solved this myself as a kid, and it's great fun. And you can represent this in symbols, and it's possible to write programs that, quote unquote, solve this problem. Here's an example of an early program in this, when artificial intelligence meant its original sense. This is a program which interacts with the user. The user is typing at a terminal and getting answers in text at a terminal. At stake is a model of a block world, kind of like the virtual world of a video game, except this is terribly, terribly simple. It's from 1970, and the world contains only a few cubes and cones and simple shapes, which are in specific positions and have specific colors. And there's some kind of arm which can manipulate them and move them around. The person interacts seemingly with natural language. So you can read the dialogue here, and there's an example of a fuller dialogue with the system, which has the weird name Shirley, in the required or the optional readings for this week. And to people who encountered this for the first time, this was astonishing. Nobody had ever dreamed of an artificial system that seemed to speak to them. This is not speaking, of course. The rule-based transformations that are necessary to produce this appearance of language use are well understood. You wouldn't stand for it today. You would recognize this as a bot talking. Back then, people were not sensitive to the idea that there might be bots talking. And it seemed to be exhibiting processes of reasoning, including things like spotting ambiguity, providing feedback, getting further information to do what it needs to do. So have a look at that at your leisure and read the lengthy transcript. But notice that the original goals of artificial intelligence and much of cognitive science has focused on our ability to reason. We introduced the rationalist concerns with the figure of René Descartes. In fact, in the intervening time, empiricist concerns and rationalist concerns have been developed in parallel, but it is the case that some research programs, some ways of laying things out, emphasize one set of concerns over the other. And at the moment, since the computer revolution, up until about 1990, I would say, strongly rationalist concerns dominated in the field. Now, we'll actually address reasoning later on in this module, but you might take a moment to think that if one were to characterize your essence, you as a person, would reasoning be the most important feature that we would need to capture? The computational theory of mind, you see, begins with a highly intellectual and abstract attitude towards human experience, something that is largely disembodied, doesn't refer to the senses, valorizes or prefers problems which we would consider to be brainy problems, solving puzzles, that kind of thing. To this extent, it favors some kind of person over another kind of person. I want to problematize all those, but this is where we're at. The field has developed in various ways, and we'll see countercurrents to this later on.